Hi everyone, my name is Alexander Beischel and I will present our paper Profiling Dataflow Systems on Multiple Abstraction Levels, which was joint work with Timo Kersten, Maximilian Bandle, Jana Gitschewa and Thomas Neumann. In our paper, we show how to profile compiling dataflow systems at higher abstraction levels so that all developers of the dataflow system can benefit from comprehensible profiling results and optimize their parts of the system. Compiling dataflow systems are very versatile and used in multiple areas, like for example in graph neural networks, as you just saw in the previous talks. However, this talk won't be about graph neural networks, but about making your life as developer of a compiling dataflow system easier during the performance profiling. And probably every one of you working on a compiling dataflow system knows the following situation. So I'm running a dataflow expression in a domain-specific language or a query in my dataflow system. Now the system parses and optimizes my query to generate query-specific code that is optimized for the underlying hardware. Then we execute this generated code to actually run the query, but for some reason it's not as fast as I would have expected. As a good engineer, I now want to figure out where my time went lost, so therefore I execute my query again, but this time I profile the execution of the generated code using perf. And now hopefully perf will tell me exactly where my time was spent, so I can tune my system again to make my query super fast. However, these are the results we actually get. And now I see that this particular line of assembly is very expansive, but it doesn't match any of the lines I wrote in the compiling dataflow system, and I can't even assign it to a part of my written query. So I'm no step further, and I will have to do a lot of reverse engineering to maybe figure out where my time was lost. But why can't we just attribute our profiling results to the components of our dataflow system like we do it all the time in traditional systems? The reason is the following. Compiling dataflow systems take a query and transfer it to a dataflow graph. Then they perform multiple consecutive lowering steps to perform complex optimizations like operator fusion or reorderings. In the last lowering step, we generate query-specific code optimized for the underlying hardware. Then we compile this generated code and execute it to actually run our query. Now, if we profile our query execution, the samples we get will actually contain results of our generated code, but not of the dataflow system. And with the attached debug information, we can assign the instruction pointers of the profiling samples back to assembly or machine IR instructions. But still, the results we see are not parts of our dataflow system, but it's the generated code our dataflow system generated with the code generation engine. These profiling results now might be useful for the developer of the code generation engine. But for any developer of a higher level in my dataflow system, they are too low level to make any use of them. Still, those developers would need profiling results mapped to their components of the dataflow system to optimize also their components. In traditional systems, if we don't know to which part a sample belongs, we profile it again using call stack sampling, for example. Then we inspect the recorded call stacks to see to which components our sample actually belongs. However, this is not possible for compiling dataflow systems. The reason therefore is the following. Our generated and executed code is actually decoupled from the dataflow system itself, because we generate this code with our system's code generation engine, then we compile it and execute it again. So in short, we have a gap between our generated code and the dataflow system itself. Now, to get comprehensible profiling results again, we need to re-establish the connection between our dataflow system's components and the generated code. And now, inspired by the way debuggers attach debug information to map instruction pointers back to lines of code, we developed tailored profiling to solve this. Tailored profiling re-establishes the connection between the generated code and the dataflow system by tracking the connection between the components of the different levels of our dataflow graph down to the generated code of our dataflow system and preserve this information of the lowering process. Then, when we profiled our query execution, we used this information to map our samples with lines of generated code back to the components of our Dataflow system. With this, we can then achieve comprehensible profiling results because we now get results for the components we're actually working on. And we do this with two main ingredients, the tagging dictionary and register tagging. Now, what we do is, during the lowering process, we already have all information available to connect the components of the different abstraction levels from the data flow graph down to the generated lines of code. But we usually just drop this information. Therefore, with tailored profiling, we preserve this connection information and then store this information in a central tagging dictionary. For each sample, we then just look up the entry in the tagging dictionary to map the instruction of our generated code in a bottom-up fashion to other components of our data flow system. And after connecting all the samples to the components in the data flow system, we have comprehensible profiling results again. So now you saw how this works conceptually, but let me just show you how this works in detail in a short example. So for simplicity, for this example, we will assume that we directly lower our data flow graph down to generated code. And we will skip all the intermediate levels and steps, but we explain them in detail in the paper. So when we now lower our data flow graph operators and generate code for them, what we will do is, for each of our generated instructions, we will store a mapping pointing from the instruction that we have generated to the data flow operator for which we actually generated the instruction. You can imagine it just like a hash table where we store for each instruction the responsible operator. And we do this for each of our operators and basically for each of our generated instructions during the code generation. So now if we have a sample with a generated instruction, we just need to look up in the tagging dictionary which operator was responsible for generating it. This works for most of our generated code. However, there is a small catch. We also generate so-called shared functions in our code. That means we generate the function once in our generated code, but then call it from multiple locations of our generated code again. For example, we implement malloc just once for our generated code, but then call it from within the scan and also from within the filter operator. If we now have a sample from executing this shared malloc function, we cannot determine which operator actually called it. So one way to solve this would be using call stack sampling. Again, we record the entire call stack, inspect it to determine from which operator malloc was called. But call stack sampling is quite expensive, and many data flow systems run on native hardware, so we have full control. Therefore, we came up with a far more lightweight solution to disambiguate such shared functions. We call it register tagging, and in difference to call stack sampling, we have very little overhead. So we just have 3% query runtime overhead instead of multiple times our query runtime, for example, sometimes with call stack sampling. And what we do is the following. We exclusively reserve a machine register by telling the compiler to reserve it so that we can only use it for our tagging itself. Then we use this machine register to tag at query runtime which operator called the shared function. Therefore, we just write a unique identification tag in the machine register whenever we call a shared function. Therefore, we enclose this function calls to our shared function with tagging instructions, which basically write the identification tag into the machine register before calling our function malloc. And then, when we take a sample while executing malloc, in addition to just the instruction pointer, we also record the content of our machine register we use for tagging. Then, if we have a sample for a shared function, in order to disambiguate it, if we have multiple matches in our tagging dictionary, we can just inspect the recorded register value, which contains the identification tag. Now, after finishing our function malloc, we just reset the register and we do the same for each call of a shared function. With this, we have a very lightweight alternative to call stack sampling for disambiguation, and now we can map all of our generated code instructions back to their higher level components of the data flow system. So now that I've showed you how tailored profiling works, let's show you what you can get from it. So we've implemented tailored profiling in our production-ready compiling data flow system Umbra, which is a relational database management system. And all the use cases you will see now are real use cases we had after integrating tailored profiling. So what we do with tailored profiling, for example, is we assign for each of our data flow operators how much time we spent for it during the query execution. So then we know exactly how expensive they are. We can also monitor the time and the activity of each operator over the entire query execution time. So therefore, we will see the interaction between different operators, also correlations, and we can even detect local bottlenecks and then optimize them. But we are not limited to any specific events, like for example, tracking the activity. But tailored profiling can handle all performance monitoring events because it basically just maps our samples back to the components independently of the event. We can therefore, for example, also profile memory access patterns by using memory load as performance event. And just to recap, we can do all of that just by closing the gap between our compiling data flow system and the generated code with tailored profiling. Thereby, we can now map the samples of our executed code back to our system's components and provide useful results for all developers. Our approach is very lightweight and has a high accuracy. We can map back 98% of all samples to our components. Further, we have little implementation overhead, so our approach is easy to integrate and also transferable to many systems. Our current implementation prototype in Umbra already works for profiling code executed on CPUs of multi-core and multi-socket machines, and now we're extending it in the future to heterogeneous compute resources and distributed systems. So thank you very much for your attention, and I'm happy to answer your questions now.